Welcome to the Explainer. So, if you've ever had to wrangle a modern microservice architecture, you already know the pain. Trying to find the root cause of a slow request, it's literally like searching for a needle in a massive digital haystack. But today, we've got the ultimate DevOps detective story for you. We're going to see exactly how Grafana Tempo lets us trace a slow request across 5 different microservices in just 3 minutes. Honestly, it's a total game changer for observability.
I mean, we've all been there, right? Your users are blowing up the support queue complaining the application is lagging and your API is incredibly slow. You frantically check the logs, but the logs say absolutely nothing useful. You just get these isolated events from random services with no clear connection to what the user is actually experiencing. Sure, your metrics might tell you the overall system is slow, but they don't tell you why. And that is exactly where distributed traces come in. Traces tell you the whole story of how a specific request navigated your entire system end to end. Let's look at how this actually works.
All right, let's jump straight into part one, the silent API killer.
Okay, let's dive into this. To solve our mystery, we need the right investigative framework. What exactly is distributed tracing? Well, the easiest way to think about it is like a highly detailed GPS tracker slapped onto your code. When a request from a user hits your system, it gets assigned this unique identifier, a trace ID. As that request travels around, from your API gateway over to an order service and eventually down to a database, that trace ID tags along for the ride. Each individual stop or unit of work is recorded as what we call a span. Assemble all those spans together, and boom, you've got a complete trace. It's a full, time-stamped family tree of the request's journey across all your microservices.
Now, you might be wondering, why use Grafana Tempo specifically? Well, it comes down to a massive architectural advantage. Traditional tracing tools, think Jaeger or Zipkin, rely on these really heavy index-based databases to store and search traces. And man, that gets incredibly expensive and complex to maintain when you start scaling up to millions of spans per second. Tempo, though, it takes a radically different approach. It uses a search-on-read philosophy, totally ditching those expensive index databases. Instead, it just stores your traces in highly cost-effective object storage, like Amazon S3 or Google Cloud Storage. So Tempo scales effortlessly, and your operational costs stay incredibly low.
Which brings us to part two, the Loki Tempo connection.
So how do we actually find the exact trace we need when everything's on fire and the pressure is on? Here's how that seamless correlation workflow operates right inside Grafana. Imagine a user reports a snack. Step 1, you spot that slow or erroring log line in your Grafana Loki dashboard. Step 2, assuming your system is instrumented properly, Loki uses a really cool feature called derived fields to automatically extract the trace ID right out of that log message. And step 3, that extraction magically turns the trace ID into a clickable button right next to your log. You literally just click it and instantly Grafana Tempo opens the full distributed trace. No manual copying, no pasting into a different window, no hunting around, just immediate context.
Moving on to part three, reading the flame graph.
Okay, so once Tempo is open, we're presented with two primary visualizations to help us hunt down our culprit. First, there's the waterfall view. This display spans chronologically. The horizontal axis is absolute time, which makes it absolutely perfect for seeing when things happen, spotting inter-service sequences, dependencies, or weird network delays. On the flip side, we have the flame graph. This view stacks spans to show their relative width. It is the best way to see where your computational resources are burning up within a single service. It helps you identify hot code paths or clunky logic at a single glance. So the crucial point here is, when you're staring at a massive trace with dozens, maybe hundreds of spans, how do you actually know which ones are making the user wait? Grafana helps us out with a brilliant algorithm called CRISP. That's Critical Path for Service Performance. In the UI, CRISP literally darkens the spans that are directly contributing to the end-to-end latency of the request. If a span is not on this critical path, spending hours optimizing it will have absolutely zero impact on the user's wait time. So CRISP cuts right through the noise and keeps our investigation hyper-focused.
And that leads us to the grand finale, the 8-second checkout mystery.
Let's actually put this into practice with a real-world scenario, something you can actually go try yourself over on Grafana Play. We've got a checkout API that is taking an absolutely unacceptable 8 seconds to process. Our investigation kicks off with just a single clue in our Loki logs. We spot this very concerning line: order processing completed in 8150 ms, trace ID equals APC123XYZ. We know the API is slow, sure, but the log itself doesn't tell us why. But thanks to that seamless Loki Tempo connection we just talked about, we just click that trace ID link to jump right into the Tempo trace view. Let's move to the waterfall view and see how this builds. We can literally track the request right down the microservice chain. At 0 seconds, boom, it hits the API gateway. Half a second in, the order service picks it up. By 1.0 seconds, it's at the inventory service. 1.5 seconds, it hits pricing. Honestly, everything seems totally normal so far. But then, the payment service makes a database call, and the timeline just stretches all the way out to 8.0 seconds. And boom, there it is. A massive, glaring, 8,000 millisecond span staring right back at us. The dark shading from our crisp algorithm confirms it. This specific span is squarely on the critical path. The payment service isn't doing any heavy computation. It is literally just sitting there, twiddling its thumbs, waiting on the database to respond. We found our bottleneck, and it is glaringly obvious. And this brilliantly illustrates the sheer depth of information Tempo gives us. By clicking into the span attributes and checking out the linked profile, we can dig even deeper into the root cause. Look at this. 95% of this agonizing 8-second wait time was spent on 50 sequential database round trips. Only 5% of that time was actual processing. We've uncovered a classic N+1 query performance anti-pattern, hiding right there in our database code. Just look at the night and day difference this workflow makes. Where we started? Well, we just knew the API was slow. We had one frustrating 8-second logline and a very unhappy customer. But where we are now? We know exactly which service, the payment service, and exactly which database call caused the whole mess. Now we can take this highly actionable finding, walk it right over to the developers, and say, hey, we need to batch these database queries to fix this N+1 issue. We went from a vague, stressful problem to a concrete, verifiable solution in literally just a few minutes. Which leaves us with a pretty provocative question for your own setup. If your most critical API suddenly failed or slowed to a crawl right now, how many minutes, or let's be honest, how many hours would it take your team to find the exact line of code causing the issue? With Grafana Tempo and a tightly correlated observability workflow, you don't have to guess anymore. The answer can literally be just minutes. Apply this kind of tracing to your own distributed systems and watch your troubleshooting time absolutely plummet. Thanks so much for joining me for this explainer.